Okay, so now we're looking at the more realistic question when there actually is friction. So we're not going to put any numbers to it. We're just going to derive an equation for the y direction and x direction. Because in the future you can just use these equations. Hopefully you can derive them on your own and be able to apply the physics to the scenario. So again, let's draw those vectors. We have force of gravity is downwards and normal force up and to the left. Okay, so what's going to happen is if the car is going to travel too slow, what's going to happen is the car will want to slide down the ramp. Okay, the car will want to slide down the ramp. So you know friction always opposes the direction of motion. So if the car wants to slide down the ramp, what that means is friction will actually be pointed up the ramp to oppose that sliding. So what we can do is we can say, okay, in the y direction, what's happening? So just like what we did last time, we have sum of the forces in the y direction is equal to 0. What forces are in the y direction? We see that Fn has a y component. Let's draw on that triangle. Here's theta. So we know the cos component of Fn is in that direction. But friction is also pointing up, so we have force of friction. But if we draw a triangle for that one, use a different color. So here is our triangle. We can see that this angle right here, that is theta. That's theta. So when we write our equation, it's actually the sine theta component. And we know this thing's not traveling up or down. That means it's being opposed by is our force of gravity. So that's our equation. So we see that mg is equal to Fn cos theta plus force of friction sine theta. Okay, so then you might have to, depending on what values are given, you can solve for different unknowns. Then the x direction, to see what happens. Some of the forces in the x direction, we know our net force is equal to the centripetal force in the x direction, because our centripetal force is directly to the left. What is causing that? You can see that Fn sine theta is to the left, but we can see force of friction is actually in the opposite direction, so minus the force of friction cos theta. So if we were to plug in some values or variables, we get mv squared over r is equal to Fn sine theta minus force of friction cos theta. So we have two equations. So we can actually just do a little bit of algebra depending on what we're looking for. So we might be looking for the coefficient, might be looking for something else, but that's how we solve it. Okay, our two equations. So now we can say what happens if we're going too fast. So let's scroll down. So if we're going too fast, inertia would want to take us up the ramp. So if we're going too fast, the radius wants to become bigger. So what that means is force of friction is actually going to be acting down the ramp to oppose that. So force of gravity is still down. Normal force is up and to the left still. Here's our theta. That's theta. So we end up with very similar equations as before. So we have sum of the forces in the y direction is equal to 0. Is equal to Fn cos theta. But this time we see that force of friction actually has a downward component. So we get minus force of friction sine theta minus force of gravity. So we end up with mg plus force of friction sine theta is equal to Fn cos theta. So that is our equation in the y direction. And in the x direction, same idea. Sum of the force in the x direction equal to centripetal force. We have Fn sine theta, but notice the friction is also in that direction, so force of friction cos theta. So mv squared over r is equal to Fn sine theta plus force of friction cos theta. So our equation is actually, they're pretty much identical. The only difference is the sign, right here, you notice that the force of friction signs, they're just flipped around. It's the only difference.